Thanks a lot. So this is the journal paper, and what I would like to do in this presentation is actually not to present all our results to you in detail, but instead of that, for those of you who are not familiar with control theory, to possibly change the way that you think about interaction. So if we think about interaction in HCI, we very often think about interaction from a cause and effect paradigm. So we have some cause, for example, a stimulus that appears on a computer display, like here, for example, in this, I would argue, one of the most successful models in our community from Card et al. And then this stimulus is processed in a number of discrete steps, in a number of discrete events, and in the end, the human executes a discrete response, like, for example, pressing a button. And if we think about motion in interaction, what we often do is we don't actually pay a lot of attention to like the complexity of motion, how motion unfolds over time. But what we often do is we tend to summarize the entire motion using some overall summary statistics, such as the movement time, abstracting from the dynamics of the motion. And this has been very successful in the past, and it has been very successful for us for designing discrete interaction. But I think that many of us in our community feel that interaction with computers is getting more and more dynamic. So what we are, for example, doing is in augmented reality or virtual reality or computer games, we are using sensors that can deliver very rich information about human motion at very high update rates. And we use that to have more dynamic interaction, for example, with physics simulation. And what we're also doing is that we are bringing interaction out of the computer into the real world, for example, with shape-changing interfaces, and with robotic interfaces, and even with interfaces, for example, using levitation. And in all of these cases, we are interacting with a dynamical system, and for example, in the physical world, we can't ignore the laws of physics, but we actually have to design for and understand the dynamics of the interaction. So what we did in this paper is we looked at the simplest case and the most well-studied case of motion, I would argue, that we have in our field, which is pointing, one-dimensional pointing with a mouse. And even if we look at this very simple case of motion, we can see that motion is actually very complex. So what you see here in this plot is that we plotted the position of the pointer over time. And in the beginning of the movement, the pointer is just sitting there, not moving at all, so there's some reaction time of the user. Then here, you see this S-shaped movement towards this target, and this is what we call the search movement. And then after this S-shaped movement, there's a number of more continuous corrective movements towards the target. There might be some overshooting. And finally, here the pointer is settling on the target, and it sits there for some time until the user finally clicks the mouse. However, just looking at position doesn't reveal the entire dynamics of the movement. So in order to do that, it's actually better to look at velocity, for example. And here in this case, we see that this initial open loop, this initial movement here towards this target, this search movement for this particular movement is very symmetric. And this is an indication that the user actually executes this motion without processing visual feedback and executes the motion in an open loop manner. We can see even more if we look at acceleration. So here you see acceleration of the mouse pointer plotted over position. And you see that in the beginning, the user builds up acceleration very quickly, but not instantaneously. Then the acceleration drops almost linearly until it gets back to zero. And what we do in our paper is we analyze, in particular, this first search movement in some detail. And our definition of the search movement is from the beginning of the movement until this second zero crossing of acceleration that you see here. So what we asked ourselves is, this motion is quite complex, so how can we actually capture the complexity of this motion formally? How can we build models that allow us to predict how this motion dynamically unfolds over time and allows us to design for this kind of interfaces? And in order to do that, you need to actually not understand interaction as a series of discrete events, but you need to understand interaction as a dynamical system, so from a control theoretic perspective. And just to give you a quick overview, we have this small framework for understanding that. And so what we have here is that we have the pointer on the display, and the pointer position is changing over time. And a variable that changes over time, that's what we commonly call a signal. And the signals in this framework are shown by black arrows. So what the user does is that the user perceives the pointer position over time continuously, but the human also has a certain intention. So the human has an intended pointer position, and what the user does is that he subtracts the intended pointer position from the observed pointer position, and this is what we can call the error signal. So this error signal is then used by the user to drive his biomechanical system, which integrates the error signal over time, and which then causes the user to move his limbs. What we can do is we can measure the limb motion or the arm motion with some input devices and some sensors, such as the mouse. And then we process this signal in the computer. So what we have in this diagram is that the stimulus appears here on the computer display, and then the response we measure here inside the computer. And now from a conceptual perspective, the critical step is that we feed back the response into the stimulus. So at any point in time, the stimulus affects the response of the user, but the response also affects the stimulus. So we cannot actually think about this closed loop system from a stimulus response or from a cause and effect perspective. So what happens if we have such a closed loop system is that we can have very complex behavior. For example, if we displace the mouse, that the overall system is able to stabilize for that and to get back on track. So based on this model, we have a definition of continuous interaction, which is if we can identify a closed continuous signal loop between the user and the interface, as depicted in our model, and the user is continuously trying to minimize the error between his intention and the system state, then we can say that the user is continuously interacting with the system. So this is not a good definition for interaction with something like button presses, but it's really geared toward interaction with mouse and joystick, where we really have a continuous interaction with the computer. So what we did in our paper is this overall framework, we instantiated that with 4 concrete executable models. So we used 4 existing models from manual control theory, which were mostly developed in the 60s, which model in particular the human side of our framework in a different way. And all of these models, they have a number of free parameters which you can identify, and then you can give these models a starting position and a target, and then they will be able to predict the pointer position, velocity, and acceleration over time. So the simplest model that we compared is the second order lag, which you can imagine as a simple spring mass system. So it models the human human arm as having a certain mass and being connected to the target with a spring. And there's also a damping term which prevents the model from oscillating forever. So this is about the simplest model that you can imagine for pointing. And compared to that, we compared a model from a manual control theory from 1967, which is a pilot model for modeling aircraft pilots. And the difference or the advantage that this model has over the second order lag is that this model can not only react to how big the error is, but it can also react to how quickly the error is changing. Then we compared to this simple open loop model, which is the Bangbang model, and this model simply assumes that the human measures the distance to the target and maximally accelerates for half of the distance towards the target, and then maximally decelerates for the remaining half of the distance, so that the arm stops exactly on the target. And we also compared another pilot model from the 60s, which is Costello's search model. And what this model is actually a combination of the Bangbang model and of the McRuer's model. So when either the error is very large or the error is changing very quickly, Then this model executes a discrete bang to get back on track. And when both of these are very small, then the model uses McRuer's model to continuously adjust the distance to the target. So we captured a data set, a pointing dynamics data set, using Fitts' law task, reciprocal pointing. And in contrast to many data sets of Fitts' law, this data set provides not only the motion endpoints, but it provides the pointer position, velocity, and acceleration over time. And I want to present you a few highlights of our analysis of the search movement in the data set, not all of the results. And one interesting thing that we found is that the time spent in this open loop search movement grows continuously with larger targets. So here you see on the y-axis you see the proportion of time that is spent in the search movement, and on the x-axis you see the size of the target. And you see that with very small targets, users spend only about 35% of the entire movement time in the search movement, and they spend most of the time actually in corrective movements. And this time grows continuously until for very large targets, obviously they spend all the time in this open loop search movement. Then what users do is that they accelerate faster with a low index of difficulty. So if the task is very easy, then in the beginning they accelerate their movement faster than if the task is difficult. And what users also do is this first open loop movement towards the target, it's not equally, the endpoint of that is not equally distributed on the left and the right of the target, but almost always the users undershoot the target with this first open loop movement. And what they also do is that if the targets are small, users are more cautious, so they undershoot the target even more. And then as the targets get bigger, they become more aggressive, and the endpoint of the search movement gets closer and closer to the target center. So this gives us some insight about the search movement, and now we wanted to actually understand how well our models are able to predict the dynamics of the mouse movement. And here you can see all four models, and you can see how, so what you see in this diagram is that the red line here, the small red line, that's the behavior of the user, and the blue line, that's the prediction of the model. And you can see that all four models are able to predict where the pointer is at any point in time with quite good accuracy. We can see some more interesting effects if we look at velocity. And here you can see the user behavior as red plots again, and the model behavior as blue plots. And you see that for the upper two models, the second order lag and McRuer's model, the phase space plot is very asymmetric. So users accelerate faster, and then the model accelerates faster, and then it slows into the target. Whereas for the Bangbang model and the search model, the phase space plot is symmetric. And looking at our data set, we can see that both models are actually good models for different kinds of users. So on the left side, we see participant 2, and participant 2 has a very symmetric phase space plot and is better modeled by these open loop models such as Bangbang and the search model. And on the right, you see participant 5, and this participant is better modeled by the continuous linear models such as second order lag and McRuer's model. So we have some new learnings about the details of the search movement. So the time spent in the search movement grows continuously with target size. Users accelerate faster with a low index of difficulty, and users undershoot the search more with smaller targets. However, what I personally feel, what really the main learning from this paper is that we really need to embrace dynamics and motion more in HCI. And this will actually enable us to do a lot of things that were difficult in the past. For example, understanding the dynamics of advanced pointing techniques and pointer acceleration functions, and also understand the dynamics of mid-air gestures and design for interaction with complex dynamical systems involving physics simulations and so on. And I think what this discrete thinking about interaction has led us to in the past is to design a lot of interaction as a series of button clicks. So even when people have designing gestural interfaces, what people often did, I think, is that they discarded the dynamics, or they didn't really take into account the dynamics of the movement, but they have a gesture recognizer that recognizes the gesture, and the end in the end creates a discrete event. So the dynamics of the gesture are discarded, and the gestures become little more than, we could say, glorified buttons. So I would hope that taking or embracing this control theoretic perspective more in HCI will actually help us to deal with dynamics in a much more principled way. And so in the past it has been quite difficult, but I think now it's getting much easier. So we provide our data set, including all this pointing dynamics for you on this web page down here, and we also provide all our models as Simulink models. So we've been using them in teaching, and they're quite easy to use. So I would hope that many people could be excited by this approach and also look at the dynamics of interaction and look at control theoretic approaches. With that, I'm open for your question. Thank you.
Hi. Ooh, sorry. Anne from Bristol Interaction Group. It's very cool work. I assume you did all the study with the mouse, and I was sort of wondering if you think this applied to other eyes, touch screens, or even like just with the fingers. How do you think it's generalized?
Yes, so I think one interesting thing is if you're looking at the dynamics of movement, you see that the dynamics of movement are very different with different input devices. And I think we haven't been paying enough attention on that. So we've been continuing this work looking at mid-air gestures, like pointing with the finger without the mouse. And the dynamics are very different. And I hope that with this kind of models, we can actually understand the differences between different ways of interacting continuously better, and also to model how different input devices differ in the dynamics of interaction.
Yeah, very interesting work. I'm Vivian Motti from George Mason University. I was wondering if you looked at the pattern of the interaction and to use that data as a predictor for the age of the user or eventual motor impairments, like could you use that for early diagnosis?
I don't know, we didn't look at that. So we only had 12 participants, and they were about similar age, but we found between different users quite significant differences in pointing strategies and movement strategies. So some users moved much more in this open loop manner, other users like slowed into the target. And of course, I think looking at the dynamics of the movement, you can probably, I don't know, I think you can find out a lot of stuff about users. But we didn't look into that, yeah.